if f is a continuous function on the interval a to b, then we let big F be any antiderivative. Now, that's because when I subtract these two values out, whatever my constant change was, that's going to cancel out as well. So I don't need to worry about the plus c's. So evaluating the integral from a to b of a function is just the antiderivative at the higher bound minus the antiderivative evaluated at the lower bound. And the notation for this is your antiderivative of x, and then we have this bar that says evaluate from a to b. So we're going to do an example here. Oh, and here's the picture. So this is why it works. So if I want to find the area from a to b here, this area, what we're saying is I'm going to take the area from everything up to b minus everything up to a. So this big f of b is the area, change color here, from here all the way back to infinity. And then I'm going to take my big F of A, which I'm going to label as a blue highlighter. That's everything up to A. So if I subtract out the blue from the red, I get the yellow. And the yellow is what I want. Okay. Now the example. We're going to find the definite integral from 1 to 2 of 4t cubed dt. So first we're going to find just the indefinite integral. And by the power rule, we have that this is going to be t to the fourth plus c. Add 1 in the exponent, divide by that. Now we're going to do the fundamental theorem of calculus. That says that I take this defined at 2 minus defined at 1. And that gets us 7. So we're just adding this evaluation part. Just make sure that you're evaluating the top number first minus the bottom number. Otherwise, you're going to get the negative version of that area. So properties. First one is the constant rule. Just like normal, you pull the constant out. You don't have to have it in here to evaluate. If I had two functions that are adding or subtracting, I can split that into two separate integrals and then just add or subtract them. Property we've seen many times before. Here, we're saying if I take the definite integral from A to itself, then its area is 0, right? If I have a curve and I evaluate it from A to A, which is just this single point, the area is going to be 0 because it's a line, right? And that line has no area. And here we have that if I have some definite integral from A to B, I can split it as the integral from A to C plus C to B. So if I have this curve, I want the area here from A to B. What I'm saying is I can find some C in the center, doesn't matter what one. And then this integral can be broken up into two pieces. I can have this integral plus that integral, and it's going to be the same. And that's true for any C. I could pick a C way out of the range. But when I take those two integrals, it is still going to work, and I'm going to get the same answer. And this last one here, 5, that's what I was talking about. If you flip the bounds, if instead of A to B, I do B to A, it's the negative version of that. So these are just some tricks that we can use when solving definite integrals. And here's that picture that I was talking about for if I have a C in the center. Then I can take this first area, which is A to C, blue, plus the red area or orange from C to B, and I still get this whole area in between. Okay. And that's something we will use down the line. Now, example 2, we're going to find the definite integral from 2 to 5 of 6x squared minus 3x plus 5 dx. So here we can split it up into 3. I can do 6x squared, then minus 3x, then 5. That's that property of adding and subtracting. Here we have our bar notation. I just evaluated each one using the power rule. So 2x cubed from 2 to 5 minus 3 halves x squared from 2 to 5, 5x from 2 to 5. And then we're going to plug in and simplify. And you guys should get 435 over 2. So here we're just taking our b's minus our a's when we evaluate it. Cool. Now we're going to look at finding the area of a shaded region on a graph. So on the graph here, we have the function given to us, which is f of x equals x squared minus 3x. And we can see that the shaded region goes from x equals 1 to x equals 3. So the integral I want to solve for is the function from 1 to 3. And that's going to give us this area. Because whenever I take the integral, it's going to measure the area from the curve to the x-axis, whether it's on the top or on the bottom. It doesn't matter. So now, evaluating this, we are going to get 1/3 x cubed minus 3 halves x squared. And now I'm just going to take it from 1 to 3. So we have 1/3, 27 minus 1, 3 halves, 9 minus 1, and then we should get negative 10/3, since that's all out there. So here I didn't specifically separate the integral and then evaluate each piece, and you don't have to. You can just write it this way. This is perfectly fine. It's a shortcut when you're writing your work, and it's completely accepted. Most people will do it this way. So here's another area. So we're going to find the area of the shaded regions. But I want to know the total area of the two regions together. All right? So I want a positive area of the two pieces. So we're going to do the same thing, finding the two areas together. But this orange area, when I go from 0 to 2, that area is going to be negative because it's below the x-axis. So before I add it into the blue, I need to take its absolute value. So we're going to set it up as from 0 to 2, the absolute value of x squared minus 4 dx. And then we're going to add the blue piece, which is then from 2 to 4. It's the same function, but I want this area to be positive so I can get the total area together. Okay? And if you do all of that, check your work, you should get 16. So feel free to pause the video, do the work, double check your answer. All right. So it's just got to be careful with this. If I want to find the total area and they want it positive, it will let you know in the problem statement. So finding area, broken down here in steps, is you want to sketch your graph. So you kind of have an idea of what it looks like. We find our intercepts. Where am I going to be finding my intervals from A to B? And divide those out into subregions, because in the previous example, we know that it intersected at the x-axis. And so because it did that, that's where our area turned from positive to negative. So, and here's what I said, that the definite integral will be positive for regions above the x-axis, negative for below. So we're going to use separate integrals to find positive subregions. That's why we did the absolute value of 1. Area means positive. We don't have negative area. So then your total area is the sum of those subregions. Now we're going to look at finding the area between two curves. Now we know how to do definite integrals. We know how to find the area under those curves. But what if I gave you more than one curve? So here's a few examples. You can see that our blue function f of x, if I took its area from a to b, it would be this entire blue region. Now I have g of x. And if I took its area from a to b, it would be this red region. But the area between both curves, meaning this area here, that's not the same, right? It's the same as taking this big area for f of x because it's on top and subtracting out this area under g of x. So we're going to take our top function minus our bottom function. That's going to minus out the area we don't want. So your technical definition is if I have two functions that are continuous and one of them is higher than the other, my y values of my f of x are bigger than my y values of g of x, then I'm going to take that definite integral, but I'm going to subtract the two functions from each other. Function on top minus the function on bottom. And here's an example. Find the area bounded by f of x equals negative x squared plus 1, and g of x is equal to 2x plus 4, and x equals negative 1, and x equals 2. So the first thing you should always do is sketch it. So here we've sketched on the right that our g of x is this red line, and our blue line is f of x. Now, we also have x equals negative 1 and x equals 2, and that we've labeled here as these up and down black lines. So where I have x equals negative 1, x equals 2, those are going to be my bounds on the integral, right? My smaller one and my bigger one, because those are my x values I want the area from. And the other thing that we need to determine is which function is on top and which function is on the bottom. And drawing a rough sketch, it doesn't have to be completely accurate, just so that you can see which one's on top and which one's on bottom. That lets you know how to set up that integral. So here, g of x is actually the top function, and f of x is the bottom. So then our integral has to be g of x minus f of x. So we have 2x plus 4, parentheses, minus negative x squared plus 1. Parentheses keep you from maybe missing a negative distributed, okay? So then we just plug it all in. We simplified it out. So I get x squared plus 2x plus 3. And when you do that definite integral, you'll get 15. Feel free to pause, do it yourself, double check your work to make sure it came out properly. If you don't want to draw a rough sketch, you can just test values. Pick a value for, we know 1 is negative 1 is our lower bound. Plug it into g of x, plug it into f of x, see which one's bigger. And you can do the same thing for the upper bound, which is 2. And you can also check and see, hey, do my functions ever cross? And you can do that by setting them equal to each other to see if maybe there is an intercept. You shouldn't have to do that, though, if they give you this, x equals negative 1 and x equals 2. Now, maybe they don't give you bounds for the x values, and the two curves are going to intersect with each other. Then the first step you want to do is set them equal to each other. the picture up here. So here we're given g of x is x cubed and f of x is x to the 1/2. And here on the sketch, we can see they intersect. So when we set them equal to each other, we can square both sides and then move the x over, factor out an x, and we have that they cross at x equals 0 and x equals 1. And that tells us what do our bounds need to be for the definite integral. So then we're going to take this integral 0 to 1, and the last thing you have to check is which function is on top and which function is on the bottom. So we can see that f of x is on top and x cubed is on the bottom. And when you do that integral, you'll get 5/12. So feel free, pause the video, do the integral, and double check that you get the same answer. Now, remember we have this plus c that I said we didn't have to worry about when we had just a regular function, the integral of f of x. And you can see here it doesn't matter either for when I have the area between two curves. Because if they're both shifted by the same constant, I'm still going to get the same area. Moving it up and down doesn't change its area. So now we're going to look at finding the area of the region. So here I'm asking for area of the region, right? Enclosed by y equals x squared minus 2x, and y equals x on the interval 0 to 4. Okay, sketch. So here's our sketch. You could draw in y equals x squared minus 2x. Then I draw in y equals x, and I put my bounds here. 0 is just that y-axis, and then x equals 4 is this black line here. Now, in this case, we have two regions, but they switch which function is on top. So in the orange region, y equals x is on top, but in the blue region, x squared minus 2x is on top. So because they flip like that, then we need to separate it into two integrals like we did for that example previously, where part of the area was negative. But instead here, we're switching it because my two functions flip who's on top, right? So our integral has to be broken into two pieces. The orange piece, which is from 0 to 3, and then the blue piece, which is 3 to 4. So here, the first one, we take the x minus f of x, right? Or blue minus the red minus the blue. X minus x squared minus 2x. And see, I have my parentheses here so I don't forget about distributing that negative. And then we add it to the second piece, which is for our blue area. So 3 to 4. But now the blue function, x squared minus 2x, is on top. And then I minus that x. So when I do those two different integrals and I add them together, now I'm going to get this 9 over 13. Okay. This is why drawing a picture is so important, because it gives you an idea of what does this look like. And again, it doesn't have to be accurate, just needs to be, semi-accurate, so that you can kind of tell who's where. And you can also do it by testing values. So it's your choice, whichever you like better. Now we're going to go into an applied problem that you guys might see in the business field. And this first one is for savings. So a company is considering a new manufacturing process in one of its plants. The new process provides substantial initial savings, with the savings declining with time t in years, according to the rate of savings function S prime of t. And that's given as 100 minus t squared. So S prime of t is in thousands of dollars per year. Make sure you're watching your labels. Okay? Time is in years. At the same time, the cost of operating the new process is going to increase with time. And then it's given its rate of cost function, which is c prime of t, t squared plus 14 thirds t. We want to know For how many years will the company realize savings? How long are they actually going to be saving things with this new process? And what will be the net total savings during this period? So if we draw a sketch here and see that C prime of t, our cost, is the blue curve, then we get that on the graph, and you can see cost is going up over time. And then we graph our savings function, S prime of t, which is the rate of savings, or marginal savings and marginal cost, because that's what we get when we do the derivative. So we can see that this blue area here, this area is going to be our savings, our total savings, as we did before in the previous homework, 7b, where we did the total. So for A, we're going to take the rate of cost or marginal cost. We see it's increasing while the rate of savings is decreasing, just like we saw in that graph. So the company should use this new process until the difference between these two quantities is 0. So where do the graphs intersect? And they're going to intersect when marginal cost is equal to the marginal savings. So we just set the two functions to equal to each other. And solving this equation gives us 2t squared plus 14/3 t minus 100. And then we multiply by 3/2 because that's going to give us this nice function here, 3t squared plus 7t minus 150. It's a easy fraction to multiply by, so I don't have any more fractions here. If I were to multiply just by 3, then it gives you bigger numbers and it's harder to work with. So now we go ahead and factor that out, and we get t minus 6 and 3t plus 25. So either it's going to be 6 years or it's going to be negative 25/3 years. But we can't have negative years, so we only want to have 6. So the company should use the new process for 6 years. Because that tells us how long is it that cost is going to be lower than savings, just like on our graph. Right? This point right here is where now my cost, my marginal cost, and my marginal savings are exactly the same. So it's going to start splitting off and we're going to lose money. Now, for part B, we want to know what the total savings are. Well, total savings is given by the area under the rate of savings curve, because that gives us total savings. That's the definite to integral for the total over our marginal, right? My total additional cost is the area under the rate of cost curve, or under the marginal cost curve. So my net savings, which is how much savings are left after I've subtracted out my cost, is going to be what is the area between those two curves between our time of 0 and 6. So that's why we want to use the two curves. So we want the area between the rate of cost and rate of savings curves, and between the lines, t equals 0 and t equals 6, because those are the time period when I'm going to be making some sort of savings. So we're going to evaluate that on this definite integral. 0 to 6. Now we take our savings function, which is on top. Those are the bigger numbers. And then we're going to minus that off from our marginal cost. So simplifying that out, we have 100 minus 14/3 t minus 2t squared. Use that power rule. We have 100t minus 7/3 t squared minus 2/3 t cubed. And then when you plug in 0 and 6, you should get 372. So our total net savings is $372. Now remember, that is in thousands of dollars per year. So $372,000. Kind of cool. Another application of area between curves is looking at consumer surplus and producer surplus. So the premise behind it is, so let's say that you are willing to pay a certain price for an item. Let's say, I don't know, $10. And then you find out that the item is actually cheaper than that. So let's say you have to spend $7 instead of 10. Well, the $3 that you didn't spend, plus all of the extra money that consumers didn't spend when they go in, because we have a price of how much we're willing to pay, but then there's the price we actually pay. That difference is the consumer surplus. And according to supply and demand, an item will sell at the equilibrium price where demand and supply curves intersect. But some customers are willing to spend more, just maybe not as many consumers. So to calculate the total amount that consumers are willing to pay for Q0 items, okay, first we have to consider where everyone is willing to pay. So this is that P0. Everyone is willing to pay that P0 price. So that intersect between the P and Q here, that's going to be our equilibrium. So the total amount everyone would pay for the price times the quantity, or P0, Q0, this is our green area here. So that's the total amount everyone would pay times the total times the quantity. This is actually the exact total that everyone together pays when the items sell for price P0. So if I divide this interval out from 0 to Q, n times, and we take that delta Q, each interval is Q people. So I'm saying is take a little piece, take another little piece all the way down, which we're doing by finding area, right? So we can do all of that, and then because we know that the area under the curves are related to our definite integral, we can actually calculate what is the consumer surplus. So if d of q is the demand function with equilibrium price P0 and equilibrium demand Q, then the consumer surplus is going to be this definite integral from 0 to Q0 of the demand function minus that equilibrium price, right? Here's our picture. I want the consumer surplus, and here's my demand curve, the blue. So I'm going to take that area from 0 to Q0 under the curve, but I'm going to subtract out this P0. I'm subtracting out my equilibrium price because this green area is what everyone would pay. And this red here is our surplus for the consumer. Similarly, we can do the same thing for producers, right? So if manufacturers are willing to supply a product at a price lower than the equilibrium price, then the lower price that they would pay, so this lower price here, this extra, say they're charging everyone at P0, if the producers are willing to sell it for less, this distance here between what they're actually selling it for and the equilibrium price that everyone would pay, that is our producer surplus. So we can calculate that as well with the same kind of idea. But here you can see that this isn't a demand curve anymore, it's a supply curve. Okay, so slightly different. So then the total area under P, or P0, is the amount actually realized. So I can take that total amount and I can subtract out my supply curve, this blue area, and that's going to give me what is the producer surplus. So it's a little bit backwards from the consumers. So here you can see we're taking that P0 price, the equilibrium price, minusing out my supply curve, and that area, which is our red area, gives me my producer's surplus. Okay? So we're going to apply it, help it make a little bit more sense here. So suppose the price in dollars per ton for oat bran is this demand function, 344 minus 3e to the q over 2, when the demand for the product is q tons. Okay. Also, suppose that S of q, e to the q over 2 minus 1 is our supply curve. So that describes the price when the supply is q tons. Now we want to find the consumer surplus and the producer's surplus, and then kind of look at what does that tell us. So the first thing we have to do is find our equilibrium quantity, our Q0 and our P0. And we got to do this by setting the two equations equal. I'm going to take my demand function, my price function, and I'm going to set it equal to my supply function. So when we do that, we got 4e to the q over 2 is 345. Divide out by 4, and that gives us this number, 86.25, approximately. Now I'm going to ln both sides, so I get q over 2 is ln of 86.25. Multiply that by 2, and that's approximately 8.9145. When we're doing consumer and producer surplus, any kind of applied problem, you are going to approximate it, right? I don't want to see ln of 86.25. That doesn't give you a price. It doesn't give you, a ton, how many tons it is. So you need to approximate it into a decimal. And now we have our equilibrium point where supply and demand are both at 8.9145 tons. Now, if I plug that into my supply function, I get approximately $85.25. This should be the same if you plug it into the demand function. You should get the same number. So P0, or our price equilibrium, is 85.25. And then our Q0, which is our equilibrium demand, that's our 8.9145. Okay. First step we need to find our P0 and Q0, our equilibriums. Now remember that we went through the consumer surplus is that from 0 to Q0 of the demand function minus that equilibrium price. Because the curve we're looking at here is, if that's our demand and that's our equilibrium price, then the consumer surplus is this piece up here. The money that they were willing to spend, but they didn't have to. So then we plug all of our information in, and we get this 344 minus 3e to the q halves. Right? Simplify everything out, and evaluating that definite integral gives us this big long decimal fun stuff, which is approximately 1795.13. You want to have your calculator with you. So now we're going to, so the surplus is 1795.13. Now we're going to do the producer surplus, which is the same thing, but now I'm taking my equilibrium price, I'm minusing out the supply, because the manufacturer or the producer is willing to sell it at a price cheaper than the consumer's equilibrium, right? So this is the price that they're going to pay. This is what people would pay. They would be willing to pay higher than this. And so because of that, we're going to minus out the supply from that price. So that's the producer surplus. So we plug in all of our data, And this time we have that integral from 0 to 8.9145, 86.25 minus e to the q over 2. So we take that indefinite integral and we use it to evaluate our endpoints. We have approximately $598.38. That's our producer's surplus. That was there. So feel free to always double check, do it yourself, check your work against the answers that we have here. So here's the actual graph. If we graph the demand function and the supply function, and our equilibrium price there is labeled in red, which you can see is where they cross each other. So the producer surplus is much smaller than the consumers in this case, because if you look at the demand curve, that's actually more elastic. You can do the elasticity formula on this, and you'll see that the demand is more elastic than the surplus is, than the supply curve. So you can see here as well, if you look at the steepness of the curves, so the steepness of the demand curve, or our blue curve, is much steeper at Q is 8.9145. And so that also will show you the elasticity. So consumers have a greater surplus when they are sensitive to changes in the price. So that's the end of this chapter. I wanted to do a couple with the applied versus, doing just regular old equations. Same process. We're just evaluating at endpoints. So again, we're going to do homework on Wednesdays, do it midnight.